happen eventually, but I forgot my space shield today, so I'm going to have to lecture with you like this. So we'll see how this goes. I just want to let you know I have, if you watched the lecture today, maybe you have, maybe you haven't, but I have reviewed the feedback from the survey, and I'm going to try to, my goal is to make this the best class you've ever taken. That's my goal. I think it should be every professor's goal. And I know there's some good comments there. There's some comments that are really positive. There's some comments of things I can work on. And so I'm going to try to sift through those this weekend and find out what are some real good things. I don't want to act upon something that, one student's idea when it doesn't represent 150. But if it's a good idea, I'm going to try to go after it. But I do want to let you know that this class is this is optional for you to be here. And I know some people say it feels like it's a 6-hour class, and I understand that. The lectures are what I would give if you're in person, and this class is going to be completely optional. So when I did only give that in-person class, people would often say in my TVALs, "Man, if you just had this session where you just do homework problems over, I'd be there every time." And now when I'm offering it, they're like, "Man, this homework session that I have just is all this extra time for me to spend on thermo." And so it's just a process that we have to deal through. And so I'll take those things and I'll consider them. And I keep encouraging feedback. If you have more feedback, it's your class. I want to help make this work. And lecturing with a math sucks. I can tell you that right now. It just sucks. It sucks. But that's what we have this morning because I didn't want to run upstairs really fast and then be out of breath. Okay, I have two problems today, and they're going to be dealing with the first law. And so the first problem is going to be dealing with a heat exchanger. And it's a special kind of heat exchanger. It's going to be called a condenser. So a condenser's job is to do exactly what the name suggests, to condense. So into this condenser at state 1, we're going to bring pressure 1 is equal to 0.08 bars, and quality 1 is going to be equal to 93.2%. So a very high quality liquid vapor mixture. It's almost all vapor, just a little bit of liquid in it. And what we're going to do is we're going to run it over some cool water here. This is going to be 15 degrees Celsius water. And that water is going to go through here, and it's going to come out as 35 degrees Celsius. And there's going to be a pressure drop here that's approximately equal to 0. I'm going to call this state 3, and I'm going to call this state 4. Coming out at 2 is going to be saturated liquid. And the pressure at state 2 is going to be equal to 0.08 bar. Okay, so there's no pressure drop as we go through this heat exchanger, but there is going to be a change in the quality. It's going to go from 93.2% to 0%. So the key thing I want you to be able to do is tell the story of the water, of the steam. I guess there's two things. There's two times things that happen here. This I'm up here, I'm going to call this the steam flow. And I know the mass flow rate of that steam flow is equal to 3.4 times 10 to the 5th kilograms per hour. And this really happens at our power plant right now in St. Mary's, Kansas. There is steam coming off the end of the turbine, and it's needing to be condensed back to liquid water. And this is happening right now. It's running it over some cool water tubes. And that cool water is coming from the Kansas River. And it's going into it has to go through some process it's processed a little bit, and then it goes through the condenser, and then it goes back out to these heat exchangers, these big heat exchangers, these big cooling towers. And you'll see all the steam come out of the cooling towers as it cools that water back, and then it'll go back into the power plant. Okay, so this is a real process that's happening. So as this hot steam goes over these cool tubes, it'll start condensing on the outside of them. And so what we're asked to do is find out what is the mass flow rate of the cooling water to make this happen. And so we have to think, if the cooling water goes through this heat exchanger too fast, what's going to happen? There's going to be very little change in temperature. It's going so fast that it's not absorbing a lot of the heat. It's just taking a little bit and leaving. So the temperature change might go from 15 degrees Celsius to 20 degrees Celsius, 25. If we go through it too slow, man, we're really going to heat up that water, and it's going to get up to maybe 45 or 55. And if we were actually dumping this back into a river, which we don't these days, but if we were, we would kill fish and wildlife, and that would be a bad thing. So there's certain environmental regulations that we have to have that our delta T can only be a certain amount. And so we're saying that this is the appropriate amount for this system, okay? So we can't go too fast, we can't go too slow, and we want to figure out what is that mass flow rate, okay? Fish depend on it. This is, we're trying to save the lives of fish right now. That's what we're doing here in Thermo today. Changing the world. Okay, which is important. I'm not trying to get. I mean, I'm not trying to minimize it. I think it's important. You know, I think it's important. All right. So to do this, we are going to look at a first law analysis. So we're going to say the change in the change in energy of this control volume with respect to time is equal to Q dot minus W dot plus the summation of my mass flow rates N times my enthalpy N, my kinetic energy N, plus my potential energy N, minus the summation of my mass flow rates exiting times my enthalpy exiting, my kinetic energy exiting, and my potential energy exiting. Now, I've written my first law equation. Steam, so can't deal with any ideal gas here. Remember, steam is not an ideal gas. It's a gas, but it's not ideal. And in fact, in this problem, it's going from a liquid vapor mixture to a total liquid. So absolutely, we can't use any ideal gas ideas here. But the question is, what is my control volume? And so I'm going to make my control volume the outside of this heat exchanger. Now, if we were to go into the power plant and see this heat exchanger, it's going to look like a big barrel. Really. It would look like a big burrito. And what we're saying here is that the heat is exchanged inside of that container. And we, although it's not specifically stated to us, we're going to say that this is not changing with time, it's steady state. The information they give to us is at steady state, that if we looked at this heat exchanger at time t, and then we waited an hour and took the same data, we would get the same data, and we looked at 2 hours, we'd get the same data. It's steady state. It's not going up, it's not going down. That's what we're saying here. That's the assumption we're making. And we haven't been given any kinetic or potential energy information, no velocities, no height changes, and there is a height change, but it's not significant enough to add enough change to our problem. The example problem I did online today shows you that even what we'd consider a significant change of velocity sometimes doesn't really change their problem too much for kinetic energy. So even though there may be some here, we're going to call it negligible. Okay, now we go back up here and we look at our heat transfer and our work. Well, work, we're saying, is there any boundary work? Is that thing expanding or contracting? Hope not. That's a 0. Is there any electrical work? Are we adding any electricity to this? No, we don't have to plug this in. It just naturally occurs because of our delta T. Is there any shaft work? Are we doing anything where we are putting in a shaft or taking out a shaft like a turbine or a compressor? And the answer is no. So we have no work here. But where students often get mixed up is this heat transfer term. This is a heat exchanger, so they think there should be heat. And the answer is it depends upon the problem statement. In this problem statement, what we are saying is that the heat is going from this high quality liquid vapor mixture into these tubes. And this is happening all inside that container. Nothing is crossing the boundary. That green boundary, there's no heat being exchanged across that green boundary. We're assuming that there's no stray heat transfer. So therefore, this actually also goes to 0. And in many heat exchangers it does, because we assume that it's an ideal heat exchanger. Now, of course, if I went to a power plant and I put my hand on the outside of a heat exchanger, I might feel a little bit of heat. But their argument is it's so small compared to the heat that's being exchanged inside of it that we can say it's negligible. Some problems that I could give to you will ask to you, find the stray heat transfer. Okay, then you're going to have to find it. But otherwise, if the problem statement does not indicate that there is any stray heat transfer, we're going to assume the simplest case, which is that it's ideal that all the heat is being transferred inside that heat exchanger. Does it pass out? Okay, that's what we want to work on. So please don't let this cue bother you. Now that we have our equation and we kind of understand, and that's where I think that telling the story of the problem is very important. If you can tell the story of the problem and get down to here, now that's really the hard part about thermo. We've just done our thermo, and now we're going to do a little bit of algebra to figure out what's going on here. So we're going to say 0 is equal to, well, we have to sum all the mass flow rates in times the enthalpy in. So there's mass flow rate 1 times enthalpy 1. And there's also mass flow rate of 3 times enthalpy of 3 coming in. Going out, there's going to be mass flow rate of 2 times enthalpy of 2 minus the mass flow rate of 4 times the enthalpy of 4. Okay, that's what we know. That's what our equation is. So I'm going to do a little mass continuity in my head because I have two things. I have two different flows. They're both water. They're both H2O, but they're two different flows that don't interact with each other. Okay, so I'm going to look at them separately. And I'm going to say that the mass flow rate of 1 is going to equal the mass flow rate of 2, which I'm going to call that the mass flow rate of steam. Okay? And the mass flow rate of 3 is going to equal the mass flow rate of 4, which is going to equal the mass flow rate of my cooling water. That's what I'm going to say looking at this problem statement. There's no place where other extra steam is added in or extra steam is taken out. No place where extra work is put in or extra cooling water is put in or cooling water is taken out. So we can make this assumption. Now, if we happen to have two different fluids, maybe a refrigerant and air, okay, which would be a good thing to ask on a problem statement on an exam because you have a refrigerant, which you use the tables to find the values, and air, which you could use an ideal gas approximation. We do look at those two flows separately. Okay, so if I do this, if I look at this mass continuity, which I did all in my head without really writing a continuity equation, we're going to have this. 0 is equal to the mass flow rate of my steam times H1 minus H2 plus the mass flow rate of my cooling water times H3 minus H4. Okay? And that is our equation. Now, what I'm trying to find is the mass flow rate of my cooling water. So now I'm going to do some algebra. I want to move these two terms on the other side of the equation. So I'm going to move the mass flow rate of the cooling water to the other side of the equation. And it's going to look like this. When I move it to the other side of the equation, it introduces a negative sign. To absorb that negative sign, I'm switched the order of my terms. So this is my equation. I could have written this way. Minus m dot of my cooling water times H3 minus H4. That's acceptable. Or I could have written the equation as this. Mass flow rate of my steam times H2 minus H1 is equal to mass flow rate of my cooling water times H3 minus H4. Or I could have written it as minus mass flow rate of my steam times H1 minus H2 is equal to mass flow rate of my cooling water times H3 minus H4. Any one of these equations is the same equation. It's a different approach, but it's the same equation. So don't hesitate to use any of these different methods. I am going to use the one I initially said. I'm going to use this one. But you can use any one of them. And so this would be a fun activity tonight when you have some friends over for a socially distanced party. You get them in groups, and you ask each of them to look at this. You give them a table, because I imagine you have 3 or 4 copies of the appendices around, and see who can do it the fastest. And they all should get the same answer, which they will be surprised about, and then you'll explain it to them. It could even be a drinking game. I don't know how you would make it a drinking game. And I don't know what you'd be drinking, but I'm sure it's appropriate. But that's just the fun you can have with thermo. I'm just trying to help you out, because college students really are, they need to get out and about. That's the thing. Socially distanced. I don't want to have to say. There's a COVID outbreak. Why? Because Dr. Wanklin suggested that we have this party with finding this. That would really suck. But I don't think that's going to happen. Okay, so we're going to find the mass flow rate of the cooling water is going to be equal to the mass flow rate of the steam times H1 minus H2 all over H4 minus H3. And now we just have to set some states. We just have to set some states here to find our values. Okay, so let's remember what state 1 was. State 1, the pressure at 1 is going to be 0.08 bars, and the quality is equal to 93.2%. Okay, so here's what I'm going to do. I'm going to go to my tables here. Go to my tables, and I'm going to my SI tables, and I'm going to go to my pressure tables for water. And I'm looking at 0.08 bars. Don't go to 0.8 bars, because that's what I did this morning at 8:30. That was a mistake. It's 0.08 bars. And I know that I'm 93.2% between 173.88 and 2,577. So my H1 value is going to be equal to HF plus X times HFG. This is HG minus HF. I could go and do this number, take this number and subtract it from this number. But the authors of your book think that that calculation is way too hard for you, so they just do it for you, and that's very nice. They subtract those two numbers and they put it right there, so you don't have to do the tough subtraction. And so we can say here that this answer, let me go back here so those people at home can see. This is going to be HF, which is going to be 173.88 plus 0.932 times, our value here is going to be 2403.1. And this is all going to be in kilojoules per kilogram. Okay? And if we type this into our calculators, we are going to get that H1 is equal to 2,413.6 kilojoules per kilogram. State 2 is pretty easy. State 2, it said it's the same pressure, 0.8 bars, but now they said the quality was equal to 0, or it was a saturated liquid. Okay, we've already looked up that value. This means that H2 is equal to HF, which is 173.88 kilojoules per kilogram. Okay, so now we have two of our values that we need. And let's remember what they gave to us for state 3. State 3, they told us They told us at state 3 it was 15 degrees Celsius water. And at state 4, they told us it was 35 degrees Celsius water. We know for water we need two things to set the state. We only have one. There are two things that we can do here to solve the problem. What are those two things? How can we set this state, these states? Liquid approximation. It's water. It's at relatively, we didn't really say what pressure it was, but we're saying it's from a lake or a river, which is atmospheric pressure. We know that water is at 15 degrees Celsius and 35 degrees Celsius. It's liquid in both situations, so we can say that H3 is approximately equal to the HF at 15 degrees Celsius, and H4 is approximately equal to the HF at 35 degrees Celsius. So I'll go to my tables, and I'll go to the temperature table, and I will look up those values for 15 degrees Celsius, 62.99. For 30 degrees Celsius, 125.79. Okay, so I'll put those numbers in. This is going to be 62.99 kilojoules per kilogram. H4 is going to be equal to 146.68. Is that what I found? 35. I looked at 30. I should have been looking at 35 earlier, sorry. When I was down here, I looked up 30, which is 125. I wanted to look up 35, 146.68. Okay, 146.68 kilojoules per kilogram. Okay, that's way one. That's the way I solved the problem. But there is another way that I would consider to be completely applicable to solve this problem. What is the other method? Any ideas? No ideas? Yes. Okay. Okay, yes. CP, well, you're saying CP, what is that method called? You're right. What is it? It's not a constant specific heat method because that's ideal gases. It's very similar to what it looks like for ideal gases, but there's a name for it. Anybody remember? Incompressible substance model. It looks like an ideal gas constant specific heat model, but it comes from a completely different place. But they look very similar here. We could do incompressible substance because it's a liquid in state 1, it's a liquid in state 2. So we could replace, what do I have here in my equation? H4 minus H3? H4 minus H3 is equal to the specific heat times T4 minus T3. And we're assuming that the specific heat C sub P is equal to C sub V here. Now, the temperatures that I have here are going to be, I would have to find my specific heat at some average temperature. So I would take 15 plus 35, which is 50 divided by 2. I would look this up at 25 degrees Celsius. Plus 273, which would be 298. And so what I would do is I would go to my tables, and I would go to table A19, I believe. I've not been very good today at my table numbers. Here is the specific heat for liquids and solids, and I would go down here to water, and here's some specific heats. Now notice it gives to me them in C sub P. But remember, incompressible substance, C sub P is equal to C sub V, so it doesn't really matter which one they give to us. And so C sub P is the one that they normally give. So I would go down here and I would say, well, I have actually my average temperature is 298, and there's not an entry for 298. But if I'm on an exam, I'm just going to say, hey, it's close enough to 4.179. So that's what I would use. I would use my C sub P is 4.179 kilojoules per kilogram Kelvin times 35 minus 15. And I would get my delta H. Let's just do that. Let's just calculate what that would be. 4.179 times 35 minus 15. This is going to give me a difference of 83.58. When I do H4 minus H3, I would have 146.68 minus 62.99, which is 83.69. See how close they are? We say, good, go for it. Either method is acceptable for me. I would not have denoted which one you could do. But remember, you can only do the liquid approximation with liquids. You can only do the incompressible substance model if state 3 and state 4 are both incompressible substances, which are liquids. If the state would change to be a liquid vapor, you can't do it. You can't do it. Okay? So now I have enough information here that I can find out what my mass flow rate of my cooling water is. It's going to be 3.4 times 10 to the 5th kilograms per second times 170, let me see here, it was 2,413.6 minus 173.88 kilojoules per kilogram. And then we're going to use this one down here, 83.69 kilojoules per kilogram. Kilojoules per kilogram cancel. And now our value is 9.06 times 10 to the 6th kilograms per hour. Okay, that's a lot of kilograms per hour, but that's our answer. So there's a lot of thermo done here, a lot of algebra done here. We have to think through and understand what the problem statement's asking. If I were in the last couple days of studying for an exam, I would not spend a lot of time doing problems, typing things into my calculator. If I had just had an hour to go through things, I would just start looking at problems and try to tell that problem story. If you can tell that problem story, I'm trusting that most of you can do algebra and rearrange some things. I mean, we make mistakes. But I'm going to give you the most points for if you can explain to me what's happening. If I see the process, that correct process, that's what I want to see on your exams. Okay? Yes, we have unit conversions we have to deal with. That's some more points. But if you can get yourself in telling you the right story, that's going to get you a lot of points on the exam. Then unit conversions gives you a little bit more. Then finding the right state properties gives you a little bit more. Okay? That's what I want you to do. Are there any questions about this? Okay, next problem I'm going to give to you is a problem I've given on 2 exams. And it's a multi-system, multi-control volume system. And so I'm going to draw it out for you. It's going to look something like this. This is a pipe. And this is a heat exchanger. And this is the throttle. And this is the evaporator. What I've drawn to you in a very, very simplified view is a refrigeration system. And I'm going to give you 3 states. 1, 2, 3. I'll give you 4 states. 4. And I'm going to provide you information on those 4 states. So, state 1. State 1 has a pressure of 120 psi and a temperature of 85 degrees Fahrenheit. State 2, all they tell us is the pressure at state 2 is equal to 15 psi. State 3, they tell us that the pressure is still 15 psi, but you've gone through an evaporator. So you've taken the substance and you've evaporated it so that the quality is 1. So it's all going to be a vapor. And then we have state 4, which is going to give us a temperature at 4 is equal to 10 degrees Fahrenheit. A pressure at 4 is equal to 15 psi. And the volumetric flow rate at 4, which is equal to 9.5 feet cubed per minute. And that's what we know about this system. I want to determine for this, what is the mass flow rate at 4, and what is the heat transfer into the system, into the evaporator, because we're going to need some heat to come into here to evaporate that R134A, which is running through here. R134A is running through this pipe. Okay, so once again, R134A is going through this pipe and coming out at these states. Now, we are going to make some assumptions. We're going to make some assumptions that the state values they gave to us are not going to be changing every second. These are steady state values, so we're in a steady state situation. We're going to make the assumption that the velocity going through that pipe it's a constant diameter pipe. It's not going to change very much. We're not going to be worried about the diameters. No kinetic energy changes. No potential energy changes. Or if there are some, they're very negligible. I look at this system and I say, there is no electrical work or power going into it. There are no shafts going into it, and the volume of it is not changing, so there's no power. It's a non-powered system. Okay, so we can have those assumptions. All right, so let me just go ahead and write those assumptions down. Assume. Steady state, W dot is equal to 0. Kinetic energy, potential energies approximately or negligible equal to 0. The only heat transfer we're going to assume is that coming into the evaporator. We're going to assume that heat exchanger is perfect, that it's exchanging heat between these two. Heat is being exchanged between these two pipes inside of it. That's it. And then we have a throttle. What do we know about a throttle? This is going to be on your equation sheet. But every time we see a throttle, we know one thing. The enthalpy coming into that throttle is equal to the enthalpy going out. And that's the only thing we know. The pressure going in and going out can be completely different. Temperature going in and out can be completely different. Internal energy can be completely different. But the enthalpy going in and out of that throttle is the same. That's what we know. Okay. So let's find out what the mass flow rate is at 4. And that seems pretty straightforward because we know the mass flow rate at 4 is going to be the volumetric flow rate at 4 divided by the specific volume at 4. And we look at this, and there's one single pipe, and so we know that if we find the mass flow rate at 4, it's going to be the same as the mass flow rate at 3, is the same as the mass flow rate at 2, and the same as the mass flow rate at 1. There's no other place where mass is coming in or out of this system. It's one pipe. So I'm doing the continuity equation in my head. I do that a lot because I don't want to write that down. Now, I will tell you that when I asked this question the first time, I said, what is the mass flow rate at 4? And students did very, very well on that. And then the second time I asked this question, I asked, what's the mass flow rate at 1? And students messed it up. Because what they did was they took the volumetric flow rate. They said, hey, I know the mass flow rate at 1 is equal to the mass flow rate at 4. So they took the volumetric flow rate at 4 and the specific volume at 1, and they divided them. Don't do that. You can't do that. You have to find everything at that one state. Okay, so if you're going to do this equation, it's got to be, everything has to have the subscript 4 on it. Okay, everything. So The volumetric flow rate is 9.5 cubic feet per minute. And I'm divided by the specific volume at 4. Now, the specific volume at 4, I have to figure out what is my state at 4. So I am going to go and I'm going to draw a quick little TV diagram. And I'm going to have my, my pressure here is going to be 15 psi. Now, here's what I did this morning. Oh, man. Those poor people at home just looked at the document camera over and over. They just looked at the document camera. I'm so sorry, people at home. I blame the people here in the class. They didn't tell me. It's your job, Miss Hess. You're going to get a tougher exam this next time. Just you. I'm sorry. So pause your screen, people at home. Take a screen cap of that, and then write me a letter, because you will. I'll get the email later. Thank you. It'll probably be about 1 o'clock in the morning, and I'm sorry. But I secretly hate you. Yes, you that is watching this video. And only you, not the other people who are watching the video. Okay. I reconsidered, Claudia. I'm not gonna give you a tougher exam. I'm over it. I'm over it now. Easy to get going, but I calmed down pretty fast. Okay, now, what I did earlier when I did this problem was I did not get myself in the right tables. I was still in the English or SI tables when I was doing this, and I got myself in the wrong place. So I was going to check myself when I did my units, but I had to make sure I'm in the pressure tables. So I go to my pressure tables, and I'm looking for R134A, and I want to see where it saturates at 15 psi. I'm not even going to show you guys at home where it is, because I'll forget to turn this thing over, and we'll have another incident. So I know that at 15 psi, we're at page A70, table A11E. I know that I saturate at negative 14.25 psi. Degrees Fahrenheit. And I'm way up here at 10 degrees Fahrenheit, so I'm going to be a superheated vapor. Okay, so I can go to my superheated vapor tables. Now I'm going to try this. I'm going to try to do this. I'm going to go to my superheated vapor tables at 15 psi and at 10, which isn't on the tables. So I'm going to have to take the average between these two values to find out what the value is at 10. That's what I'm going to do to find out what the property is, what the specific volume is at 10. So I can do that. And so to do that, I am going to say that that's going to be 3.0893 plus 3.2468 divided by 2. That's going to be 3.1681 cubic feet per pound. And so that'll give me a value of 9.5 divided by 3.1681 is going to give me 2.9986. It's basically 3 pounds per minute. Or if I say that in 1 minute or 60 seconds divided by 60, I'm going to get 0.0498 pounds per second. That's my mass flow rate at 4. Okay? Again, people lost a lot of points when I asked for what the mass flow rate at 1 was. Okay, now I have 6 minutes. And one of the things that they asked me to do on the video, on the survey was slow down. Yet people still watch my videos on YouTube at 2x. So I don't know what's going on there. There's a dissociation with what's going on there. Okay. Now I want to find out what the heat transfer is coming into this. And so what I'm going to say is, my first suggestion is I'm going to make the evaporator my control volume. Okay, if the evaporator is my control volume, I can set the state coming out of that control volume, but I can't set the state of the R134A going in. I only know the pressure, not enough information. Okay? So I have two options here. I can try to find what the property is at 2, or I can make another control volume. Okay? So here's what students do on this problem. They say, well, I don't know what it is at 2, but hey, there's a throttle there. Throttle says the enthalpy before the control volume, the throttle is the same as the enthalpy after. And if I set that, I know my state, and I can go down here. Let me write my first law. dE dt is equal to Q dot minus W dot plus, I'm just going to do it this way. Mass flow rate in, enthalpy in, minus mass flow rate exiting, enthalpy exiting. Look at all that stuff I skipped off. I already took out kinetic and potential energy. I just skipped because I know I have 5 minutes left. Okay, I just skipped all that. And that's fine to do. I want to go through all this, but it's fine to do. And I know I'm at steady state, so this goes away. And I know I have no work, so this goes away. And so I'm going to say that 0 is equal to Q dot plus m dot times h1 minus h2, or hn minus h exiting, I should say this way. Or by heat transfer is equal to m dot times h exiting minus h entering. Okay? I know if I make this small control volume, I know my h exiting, but I do not know my h entering. But they say, hey, there's a throttle. If I find the enthalpy at 1, which I can find the enthalpy at 1, then I know the enthalpy at 2. And the problem is that's a really, really bad idea. Because what happens is the R134A at 1 goes through a heat exchanger and completely changes. And it comes out here at state A. The enthalpy at A is the same as the enthalpy at 2. But the enthalpy of 1 is not the same as the enthalpy at 2. So that's the biggest mistake that happens on this problem. Now, can I find the enthalpy at A? Absolutely. I could make my heat exchanger my control volume, and I could say I know what's coming in at 1, I know what's going out at 4, and I know what's coming in at 3. I can find my unknown and my unknown A, and then use the throttle. So I could use 3 different control volumes to solve this problem. First, a heat exchanger to find A. Then a throttle to say that the enthalpy at A is the same as the enthalpy at 2. And then finally, now that I got the enthalpy at 2, now I can use this equation with 2 and 3. That is a way to solve the problem, and it would be an accurate solution. It takes you some time. What I would suggest is instead of making the control volume, that yellow control volume, now what we should do is think about this. What if I made the control volume this entire thing? If I covered up that state 2. Now, in this big control volume, I know what's coming in here at 1. I can set that state. I know what's coming out at 4. I can set that state. I don't have to care at all. This dang mask sucks. I don't care what's going on at 2 or 3 because that's inside my control volume. But I do know that heat is coming into that control volume still. So that's one control volume that I have to solve one problem and not do 3 different problems. And so we're going to be practicing how to do this coming up here, how to select an appropriate control volume to solve a problem. And so here I have Q dot is equal to mass flow rate times H4 minus H1. Okay? Now, H1, we don't really know. H4, we know it's a superheated vapor because we found it already. We have found the specific volume at 4, so we would know H4. So H4, we're going to have to do the average thing again because in the superheated vapor tables, we only have 0 and 20. We'd have to average it, and I get 104.38 BTUs per pound. H1, I'm going to have to figure out if it's a liquid, a vapor, or a liquid-vapor mixture. And so what I'm going to do here is I'm going to draw my vapor dome, and I say that it's 120 psi. At 120 psi, I know we saturate at 90.54. I know my temperature's at 85. So I'm a liquid. There are no liquid tables for R134A. Because there's no liquid tables, I have to say that H1 is approximately equal to the saturated liquid enthalpy at the temperature of 85 degrees Fahrenheit. The liquid approximation, and that's equal to 38.99 BTU per pound. And now I can just plug these things in. I can plug this into here, and I can plug this into here. With my mass flow rate, I found that my heat transfer is going to be 11,764.97 BTUs per hour. Okay? That's how much heat must be added to the system for this refrigeration cycle to work. Okay? That is the second problem, and I've overrun my time by 2 minutes. And I sped up, things that things that the surveys say don't do, but some things I guess are just me. So if you have questions about this, please don't hesitate to come and ask. We'll be doing problems just like this in the lecture, the video lecture on Monday, and in the in-person section on Monday, and the in-person section on Wednesday. So we're going to do a lot of problems about finding your control volume, making decisions, telling the story for the problem, okay? 1 week from next Monday is our it's our second exam. Doesn't it feel like it should be our third exam? Because this semester has just been forever. But okay, have a good weekend. Let's beat Texas Tech.